Okay, my outstanding friends, this is extremely important. Do not, in your life, do not click off of this because it could save your life. This is a doctor. This is Dr. Eric Berg. He seems to be a heck of a nice guy. He's looking to try to keep people healthy. I am not a doctor. I am not a doctor. I don't give medical advice. I am a researcher. I am a chemist. Basically, I was an electronics guy my whole life, and which is nothing more than chemistry. And this is just basically chemistry and how things interact with each other, molecules and so forth, which is just exactly what your body does. And then it goes into, you know, the resonance theories and molecular orbitals and all of this different. This is my background. And then it gets into thermochemistry, where heat takes a big part. It makes a big change in how things react. And of course, magnetic properties and all this, intermolecular forces. And I'm just, the reason I'm going through this is I want to establish a little credibility. And I always said the transfer of energy from light is to atomic vapor. Light is nothing more than atomic vapor. That's my other theory. But anyway, this is my background. So he is a doctor. I am not a doctor. I am not a doctor. So do not take my advice medically. I will show you what the research says, and then you're on your own. Okay, you saw the title. Can these little colors save your life? And let me tell you what, these colors are your life. If these colors were not in your blood, you are dead or extremely ill. Because these colors, you see these 2H, 3H, 5, 6, 7, all these pluses, these are oxidation states that these molecules can take on. They're called transition metals, and they work in aqueous, which is wet, watery fluids, and they flow through your blood along with all the rest of the particles in your blood, and they pinch things. That's how come they see 2, 3, 4, 5, 6. They can pinch different molecules, because different molecules, different atoms, have different numbers of electrons. These have a ton of extra electrons, so they only need 1 or 2 to fill up to what is considered the rule of 8. These here have only 1 or 2, so they need like 6 or 7 to fill up. So these are the things that transfer. These are the transition metals. They sit right in the middle. They say, okay, you guys can go over there, you guys can go over here. I'll work you. I'll take care of it. I'll move you back and forth. I am the transitioner. I am the transferer. I move things for this side to this side and that side back and forth. And I make you stable. I make you stable. But as you're living, you're dead. You're 100% not stable. You are not stable, and not one single molecule in your body, outside of possibly enamel on your teeth, is not stable. Not one single atom, not a single cell. It continuously is giving up oxygen, giving up carbon dioxide, taking in oxygen, passing back and forth, garbage out, good, glucose and so forth coming in, vitamins, minerals, all the things to make your body function correctly. Literally to feed the bacteria, because the bacteria, I'm going to tell you right now, the bacteria is basically everything in your body. The bacteria does all the jobs in your body. It breaks down all the chemistry, it fights off all of the invaders, it creates mucus to make slime wherever it's being attacked in your digestive system. Every single membrane in your body is loaded with bacteria. And if you don't have that bacteria in there, you can't fight anything off. It just comes right through. That's the protective layer in your body, and it's called interstitium, and we're going to look at it. But this is the protective elements in your body. If you don't have these, you're not going to be healthy. You're going to be sick. That's why they say, well, he's got anemia. Why has he got anemia? He's iron deficient. Why is he iron deficient? He doesn't have enough iron. Fe. Why would that be a problem? Well, because he can't create these +2 and +3 states. Well, so why is that? Well, that means he's got a problem transferring oxygen from the +2 to the +3 state, which is to take on oxygen. Well, why is that? Well, I don't know. But I can tell you what, I'm almost 100% sure it's got to do with something in the microbiome that converts the stuff you eat into these particles. Those bacteria are down there, and they know exactly what to do. And they will do it just day after day after day after day after day. If you have the right products coming into you, so your diet is pretty important. But more important is the bacteria that resides down there, because those are the workers, those are the chemists, those are the guys that deliver and pick up and do all of the things in your body. And they create enzymes and catalysts. And you know what a catalyst is in an enzyme? Let me tell you what they do. Well, let's just go and read about it. All right, don't forget, this is my area. It's chemistry and all of the, we're going to be talking about ligands and these transition metals and the complexes that they form and how they transfer elements through your body to keep you healthy. And what is used is catalysts and enzymes. They are different, but they are associated. Now, let's just go down through them. Enzymes and catalysts both affect the rate of a reaction. And that reaction is what your body's doing. It's reacting to the chemistry as you need it. If you need products, it reacts, and it creates these little enzymes and catalysts that go break things up and provide them to your body in a form that your body can use. And that's all done by bacteria. Now, and that's what I don't think they understand. They think your body just does it accidentally. I'm telling you. Anyway, the difference between catalysts and enzymes is that enzymes are largely organic in nature and are biocatalysts, while non-enzymatic catalysts can be inorganic compounds. Neither catalysts nor enzymes are consumed in the reactions they catalyze. They are there as little chemistry sets to go out and break things up and do exactly what they're supposed to do, and they just wait around to do it some more until they've cleaned up the mess, and then they're consumed and they go out of your system. It's an absolutely unbelievably elegant system. Now, what's the difference between a catalyst and an enzyme? Guess what an enzyme is? An enzyme is exactly identical to a virus. All right, a virus, we'd say, ooh, he's got a virus. Well, you got millions of viruses going on basically in you right this minute, because all of these enzymes that are in your body break down things so your body can use them. Well, guess what? COVID got into your body, and your body should know, hey, I don't want that thing here. Get it out of here. Well, your body's never seen it before. It says, yeah, let it in. Yeah, I don't know anything about him. Let him around. If it gives us trouble, we'll get rid of him. Well, guess what? He's so much trouble, this COVID guy, that he gets in there and starts to break up collagens, which is the rubbery things that make your blood vessels work, make your heart pump, make your lungs expand and contract. That's the rubbery things it breaks, and it breaks them into fibrosis, fibrotic little pieces. This is what the research says. Now, I'm not saying do anything, yes, or don't do anything. This is what the research says. People are getting fibrosis and fibrotic reactions, COVID toe, clogged arteries. These are the long haulers, and this is what this Dr. Berg is going to be talking about. And I like the guy. I subscribe to him and I watch his stuff. He's very, very informative, and he seems like a heck of a nice guy and wants to do what's right. And I hopefully can help in some respect, because this is my area. I understand the chemistry here, and I've been working on soft tissue preservation for my fossils, which I'm going to show you right now. It's kind of, well, this gives me you'll understand. This is a goose. You see the feathers, the pattern of feathers in that goose's head? That's a goose. All right, and you say, well, how did that thing turn into stone? What could have possibly caused feathers and a goose to turn into stone? Well, why is it different in the inside? You can see the neck and the throat and everything. If you know how to look at things, the architecture of it, and how it would have died laying like this, and it was in a flood, flat as a pancake. All right, so, and I have a bunch of other ones, and I have other ones DNA tested and certified as actually human, and they are stone right now. And I could show you that, and I suppose I should, just to verify a little deeper. But this is my background, is chemistry, atomic physics, nucleuses, all of that stuff. How does bonding work? How does the interaction of molecules? And this is what's called nucleophilic substitution. This was not understood as a biological process, and it still, I don't think, is, because as far as I can see, because nobody's talking about it. And anyway, it is a biological process, and it's happening in you every second, because everything is called, there's leaving groups, and they call them nucleophiles and electrophiles. It's the leaving groups and invading groups. So something comes in and replaces something was there, and that goes out. This is exactly what happens with carbon dioxide and oxygen and glucose and all of these different urine and all of these different biomolecules that are in you. That once they're consumed, they got to get out of there. They call them oxidative stress molecules, and transition metals are oxidative absorbers. Let me show you that. All right, now, the research indicates the body is literally a dance between bacteria. Good bacteria, bad bacteria. The good bacteria protect you. The bad bacteria break down all kinds of things and try to invade you. They try to make a life for themselves inside of you, just like the good bacteria. But the good bacteria can protect you. However, they all work with antioxidant transition metal complexes. These are the things that suck up the oxidation states. Okay, as I said before, an enzyme is basically a program. It's a bacterial type of program, and it invades what's called the ribosome, I believe, and at that point takes over the cell mechanism and creates whatever it tells the cell to create, because it is the messenger that comes down and says, here's the program, start making this stuff. What it makes is catalysts. And a catalyst is nothing more than a little chemistry set, very, very simple, well, not simple at all, extremely elegant, but very specific. Now, here's what it says about enzymes. And they occur naturally in living organisms. They're just everywhere. Now, enzymes can increase reaction rates by enormous factors, up to 10 to the 17th. That's like bazillions of times faster than an uncatalyzed rate, because they're going to do the same sort of thing, but the catalyst comes in and says, hey, let's do this all right now. Done. And I'm talking to you millions per second, and it doesn't even use up the catalyst. The catalyst does another one, another few million the next second. And when it's all done, it just goes away. And these catalysts tend to be very, very specific, typically producing only a single product. So it might produce carbonized zinc, or so it might produce some specific exact product, only one molecule. It will end up yielding only one molecule style. All right? They are the focus of active research, because if they can design these enzymes to create whatever they want, they can create exactly that exact product every time. So at the same time, enzymes are usually expensive to obtain. They often cease functioning at temperatures greater than 37 degrees centigrade. Now, why would that be exactly 30? You know what temperature that is? 98.6 degrees. That's body temperature. So they stop functioning at temperatures greater than 37 degrees. Now, that's interesting, because that's body temperature, 98.6. And when you get a temperature, when you get an infection, and you get you start sweating, and you got 101, 102, 103 temperature. Well, obviously, they're not going to function at those temperatures. So that's kind of interesting. This is the first time I knew about that. When I saw 37 degrees, I said, whoa, and I looked, 98.6. So then they have limited stability in solutions. So they only last so long in solutions, but that's because once they've done their job, it's done. They have such high specificity that they are confined to turning one particular set of reactants into one particular product. They throw a whole batch of stuff at them, and they break it all down, and they say, all I'm going to make is hemoglobin, or all I'm going to make is iron, or all I'm going to make is copper, whatever it is. So they're very, very specific. This means that separate processes using different enzymes must be developed for chemically similar reactions, which is time-consuming and expensive. They want to use it to create things they can exploit, in business. All right, this is what it is. This is about business, but I'm looking at it as what's called nucleophilic substitution. See, these are what the processes, commercial processes, Union Carbide and all this stuff. These are the transition metals primarily, which are involved in the catalyst because they create metal complexes, and then the reactants, and then the final products. So there's it breaks them down into all kind of different little products, and until they get to the end product, which is what they were designed to do. You see all the different, iron, chromium, copper, aluminum. These are all your different transition metals, and that's what catalyzes things. And that's the only way, and the reason is because they have deep orbitals that can be filled with electrons. That's what I showed you in the beginning, those +2s, +3s, +4. Those are inside the valence shell, which is the outside orbital. Usually you have to fill everything up until you have only the outside has a few little blanks in it. Well, these have deep orbital holes, so they can attach to sophisticated chemistry that other things don't attach to. That means they can drag them over, drop them, drag them over here, drop them, drag and drop, drag and drop, drag and drop. That's why you stay alive. Once your body is no longer functioning, pushing blood, which is where these transition metals reside. This is your blood. Once that stops moving through there to bring in the good stuff and take out the trash, it's all over for those molecules, and they normally rot and get taken over by bacteria and so forth. However, in the case of my friend here, Caesar, he got caught in what I'm going to call a saltwater flood. And he was apparently drowned, and I now think he might have been in a hot water situation. I'll explain that later. But he died flat like this. This side here has no articulation to it. It's just flat. This side is his head and his neck. And his neck is, if you know how, you can see, maybe you can see, maybe you can't. If you have eyes to see, you have eyes to see. If you don't, you don't. That's his neck right there. And that whole thing right there, that's basically his throat and neck and the bones and all that stuff around it. But it's been through the process of nucleophilic substitution. And that happens in wet, salty waters primarily because of the transition metals. They move things back and forth until the molecules that were here say, hey, can you bring me something to make me stable, the flesh? And it says, yeah, well, I have to bring in some, whatever it is, it creates basalt. And all that is basalt now. And all of these have been, it's called nucleophilic substitution. Look it up. You have to do some work on your own. I can't fill your head with all these stuff. I've done my work. My work is done. And I understand this. And feldspar is not just some coating that coats stones, because inside is basalt or limestone or whatever it's going to be inside, all kind of different stuff inside. But the outside is this collagen material, which is nothing more than membranes. Skin, membranes, that sort of stuff. Like this bone, that's a bone. All right, and it's a bone. And what it is this is what's called periosteum. Periosteum, I believe. And the ancients used to call it tunica, which is the membrane that wraps the bone. Everything has to be wrapped in its own membrane. And inside that membrane, it's saturated with bacteria. Every membrane in your body and every square inch of the membrane is loaded in these pocket-filled bags called interstitium. Something that has just recently been understood, and they still don't understand it, is literally the source of your immune system. Okay, so I think I probably got a little off course, but everything here is important to understand. That catalysts, enzymes, all of that stuff is controlled by the interstitium and the membrane-bound bacteria. Now, he's going to get into that, and I am going to comment as he talks. I watched a little bit of this, so I feel a little comfortable being able to discuss. He's going to be going deep into some chemistry. But let me show you the interstitium and why it's so important. All right, this is from pretty recent research. This goes back to 2016. They discovered that inside, underneath every single membrane in your body, 100%, every single one, has these fluid-filled bags and these little springs and these walls. And these latch down. These are the anchors. These are the springy things that keep the bags opened up. And the bags are these inside these floppy-filled little collagen bags. And inside here is fluids. They call it interstitial fluids, which are the membrane-bound bacteria live in here. They're saturated in here, absolutely soaked with bacteria. And not only are they in their bags separately, that is what's called an interstitial highway now. This is just being understood. And the reason they finally figured this out, that they know this stuff travels through, because if somebody gets a tattoo up here on their skin somewhere, they will actually be able to find remnants of that on the organs and all through, completely through the body. So they know the stuff travels through these fluids and not just stuck in one little bag. The ramification of that is that under, like this, they call this mucosa. Now, all this is the separation between whatever's bad out here and whatever you want to keep separated away. It's a membrane. And that membrane could be your skin. It could be, in the case of this goose, it's the feathers. It's the same stuff. This is made out of collagens, which is nothing more than that. Anything that protects you from the environment. And it's very stable stuff too, the collagens and so forth. So what am I getting at? If you don't have the membranes saturated with the good bacteria, here's what will happen. You will get something trying to attack you here through this. And here's what should happen. Your bacteria in here should say, whoa, 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 what are you doing out there? Get out. And it squirts some slime or some oils out at it to get it out of there. Just don't let it get in. Well, if that didn't work, it says, I can get out of there, I'm going to dig through that, and it's some kind of nasty thing, it shoots out a chemistry set. And that chemistry set will go out and break that guy's legs. And that's exactly what happens. It goes out as just as I showed you, a specific molecule that your body knows that molecule will break that particular place in that particular invader, and it will die. Now, if you're invaded all over your body, you're immunocompromised because you don't have any of this bacteria living in your lungs, in your heart, in your intestines, in your blood vessels, and every single bit of those has to have it. And usually when you lose a species, it not only does your lungs, it might do your throat, it might do your heart, anything that is rubbery, because that's what these things do. And then the springs will break. And then the springs are the fibers. That's my take on it. That's what the research indicates. Again, only research. Now, so what do we have? That's the takeaway. Membranes separate bad from what you don't want it to get into. This could be poop. This could be blood. But the blood and the poop and everything has good stuff in it too. Your poop, you use all that stuff, but you got to get it broken down outside of your bodily fluids and tissues. So that's where your intestines come in. It's a barrier. Stay out. Mucus all over the place. Slime everywhere. Stay away. Stay out there. Do your job. And if I see something out there I want, I'll send a guy out for it. And that's exactly what happens. The membrane goes in and it goes out. And there's all kinds of ion channels, and they really just don't fully understand it yet. But they're working on it, and they're doing a good job. I'm not criticizing anybody. It's very, very complicated. And it's just now being understood as a nucleophilic substitution invasion allowed. So, you know, and that's what your body does all day long. It allows these invasions of chemistry. It says, take out the trash, bring me something good to eat, I'm starving. And he says, well, okay, it comes down and it gives you, like whatever it's bringing in for nutrition, And it says, I got some nasty stuff laying over here. Get this out of here. And it grabs a hold of that, and out it goes. And then it goes into your poop, your urine, whatever. Your liver goes out and takes a lot of that stuff and reformulates it back into something you can use. I believe that's the function of the kidney, the liver, well, the kidney too, is to clean things up. So this has to be understood as this process. You need slime, you need these catalysts and enzymes to go out and attack the things that are trying to attack you. You got to send them out to break down the food. You eat something, and it will know. Literally, I think you're connected so much that when you eat something, your tonsils and so forth, way up in your mouth says, hey, get ready down there. The guy just ate a burrito. He just ate some chili peppers or something. And it sends down messages down to your guts and says, get ready. Get the chemistry ready. This guy's in trouble here if you don't do something. He's going to have heartburn. He won't be able to sleep all night. And that's what happens. Now, if your chemistry's there, if your bacteria is there, if the transition metals and the mucus and all that stuff is there to do its job, you're okay. But if not, it literally can burn through your mucosa, through your membranes. If you can't slime it out of there, this is the problem. That's what the research indicates. And probiotics seem to be extremely valuable. And the National Institute of Health claims that they even help with this new nasty virus that's been attacking and killing so many people. And I think I understand why, because it is breaking down the collagen that opens these bags up. So your lungs can't open back up again. You breathe out and it collapses and it can't open. And then these little fibers break and they float through the system. And they're giving it COVID toe, people are having skin conditions, the long haulers, because they still don't have the bacteria in these fluid-filled bags. Now, I don't know if they can rebuild these after they're all broken down. I just don't know. Are they long haulers forever? Will they ever get better? Je ne sais pas. But I tell you what, without the bacteria in these fluid-filled bags, you're a wide-open target for invasion. And once there's types of bacteria in you that don't just live right in that one bag, and this guy's in the other type, and this guy's other. No, if it's in a certain layer of the tissue, which is, say, your digestive system, your acids in your stomach, that's a certain bacteria that's not going to live where your heart muscle is, or where your where you understand what I'm saying. There's all kinds of different bacteria, and they are literally designed to live just like they're supposed to live in these little houses that are in the colon, in the intestines. All of your tendons, your muscles, your organs, your eyelids, your eyeballs, your nasal passages, your throat, your lungs, every single one of them has a different type of bacteria. And the people that are getting infected by a lot of these novel diseases, which is something your body has never seen before, so there's really no reactivity to it. It says, hey, I don't even know what the heck this thing is. We got to figure out a way to deal with it. That's what's called your immune system. Once you lock that in, how to deal with this invader, it goes into a place that's called CPG islands in your junk DNA. And that CPG island remembers the chemistry set that attacks that. When it gets queried to say, hey, I got this particular type of virus that I saw 6 years ago, do you remember the chemistry set? Oh yeah, no problem. Comes back down, out it goes, dead. That's what immunity is. Now, nobody's ever seen the COVID. So this is all new. So it goes up and say, hey, ever see this thing before? Nope, no clue. What are we going to do? I don't know, man. You better do it quick. That thing is really playing havoc on this. It's collapsing the guy's lungs. They're not going to live. You got to do something quick, and he doesn't know what to do. Now, probiotics, though, flushed into the system, appear to have a positive effect. And that's what the National Institute of Health says. And I'll show you the article right now just to back me up, and you can go look at it yourself. It's very interesting, I thought. Now, somebody should ask Joe Biden tonight on his town hall meeting, why is nobody talking about this? Probiotics and the prevention and treatment of this new novel disease, current perspective and future prospects. It says in the conclusions, it's very, very supportive of probiotics. Here's the conclusions. Probiotics-induced suppression of the inflammatory cytokine response may prevent both the severity and occurrence of acute respiratory distress syndrome, making probiotics an attractive add-on. And it goes down here, it says, therefore, supplementation of probiotics in high-risk and severely ill patients and frontline health workers might limit the infection and flatten the COVID-19 curve. However, there's no current random controlled trials. Why are not we doing this? This goes back a while, and this was known 10 years ago about probiotics. I mean, in National Institute of Health, same thing. 10 years ago, I had basically the same article. And it says that they have to flatten the curve and the foremost priorities during the ongoing pandemic. And it just says how to flatten it. And I haven't heard one single word about probiotics, not one single syllable. So that's kind of upsetting to me.